Okay, welcome everybody. It's been a little hard for me to figure out exactly where to start, how to proceed. What I'm going to do is start very basic and maybe proceed a little quickly, so we don't jump in the middle of something and lose anyone. So you should have these slides. I sent quite a lot of material. I don't know if you were able to look at some of it. Basically, I'm going to go through those things and try to proceed quickly, but please do ask, stop me and ask any questions you might have, because sometimes if you get lost, you stay lost. So it's really important to say, stop, I have a question I didn't understand. Okay, so just a couple of introductory slides here. Traditionally, when I was a boy, which was a very long time ago, economics consisted of analytical theory models, something you can solve with pencil and paper, an econometric estimation and testing, and there really wasn't much in between those things. And then simulation modeling began to develop in the 1970s. And it's really a complement to the others, not a substitute. Really extends the reach of theory to problems that are analytically impractical, that cannot be solved analytically. It extends even the usefulness of econometrics by allowing counterfactuals on calibrated simulation models. Typically, in formulating economic models, there's two ways we go about it. One is as constrained optimization problems, and the other is economic equilibrium problems, which are some sort of square system of equation inequalities and unknowns. The limitations of analytical theory arise from a number of reasons, just dimensionality, computing corner solutions, and a variety of other things. So I always love to confront skeptics. I don't think anyone listening in on this course is a skeptic about simulation modeling, but I have this great quote that I found once from John von Neumann. Whenever I'm dealing with econometricians or especially analytical theorists, I like to put up this little quote. It goes way back to 1945. He was actually talking about partial differential equations, but hey, that doesn't matter. The point is that analytical methods really run out of steam very, very quickly in very small, specialized, lower dimension models. Okay, I guess I sort of said some of this. But the reason analytical methods tend to fail, first of all, functions or equation systems have no closed form solutions. Large dimensionality can't be handled. Correct models consist of nonlinear weak inequalities. Analytical methods tend to impose the requirement that you have some kind of corner solution typically. And a lot of the analysis in analytics is local, very small differential changes. But that's not what we're interested in for policy. We're interested in large changes that may move us a long way from the initial equilibrium and involve changes in what sort of trade links are active or inactive, what technologies are used or slack. And so these corner solutions and nonlinear inequalities are really important to do policy with large changes. That's why we have developed simulation modeling so that we can handle these different things, whether it be in partial equilibrium or general. Okay, so structure of a typical model, a theory model, usually based on the assumption of optimizing agents, so consumers, firms, and governments. But the problem is generally the model cannot be written as a simple constrained optimization problem just maximizing or minimizing one variable. That approach quickly breaks down because you have multiple agents that are simultaneously optimizing, and you have industries, firms, consumers, maybe governments have objective functions they're optimizing, and you can't treat equilibrium as the solution to a single optimization problem. It just doesn't work. And lots of issues of taxation with redistribution. Got to be really careful. Optimization can give you the wrong result. So the kind of models we're going to work on are typically embody optimization at the level of the agent. So each industry is optimizing, each household is optimizing, maybe governments are optimizing over taxes, tariffs, and so forth. We end up with a system of equations, or rather weak inequalities that we'll see, where the optimization is embodied at each level of those agents and equations. This is, again, I gave you some pre-course notes. I don't know if you were able to look at them. I had an awful lot of stuff. So what we do in each case is convert the optimization problem of a household or firm or even government into these inequalities and equations, converted into a square system. And the underlying mathematics of this, especially in GAMS, is very well defined. GAMS solvers are derived directly from the Karush-Kuhn-Decker theorem, which converts an optimization problem into a system of equations. And then there's other tools such as the implicit function system, which says you can explicitly solve for endogenous variables as a function of parameters. And that becomes very difficult. It doesn't work very well in large dimensional models. So what we are going to do is use KKT functions to derive cost, expenditure, and indirect utility or profit functions. And then those in turn are the derivatives of those via something called the envelope theorem and Chequers lemma are used to derive, say, demand equations for factors and goods and supply functions, et cetera. So the whole setup in GAMS and the way we use it, and the way I've learned from Tom, is very much rooted in good economic theory, which makes the tools very powerful, I think, very robust to a lot of things we'd like to do that can't really be done some other software. So some of the difficulties in these big models are the dimensionality, inequalities, and bounded variables. Again, I'm repeating myself a little bit here, but traditional analytical methods break down very quickly past extremely simple models, even in this, what the economists love, which all get taught in undergraduate international trade, the Hexrell model actually does not have an analytical solution. And that's only two goods, two factors in two countries. Another problem with analytical methods, based on the tools of calculus, is that our economic variables are typically bounded. Prices and quantities have to be non-negative. And so economic equilibrium conditions are weak inequalities. So examples when we get to do big changes in policy analysis, what goods are produced, what technologies are used, which are slack, what trade links are active in equilibrium and how can they trade. You might even have policies that reverse the direction of trade, and you want to be able to do that software formulations and CAN models can't do that. We have policy tools that may or may not have a positive price, like emissions permits. If there's excess supply, price is zero, so forth. Okay. And alternatives to this complementarity framework is that, and I'm not sure if this is true in GTAP, but their model, you have to assume the strictly interior solution. Or
So they have methods for dealing them, but it's a very special case. So there's a specialized, you have to basically be very, whereas here it's the default treatment is if there's a boundary, then the model comes in. So you, as you'll illustrate here, right?
Okay. So the framework we're going to be working on this week is nonlinear complementarity. And this is derived from the Kuhn-Tucker theorem and nonlinear programming. So we have weak inequalities. Each of them has an associated variable, typically a non-negative variable such as the price or the quantity, and that's called the complementary variable. So if the if the weak inequality holds as a strict equality in equilibrium, the complementary variable is generally strictly positive, except it's a knife-edge case. If the inequality holds as a strict inequality in equilibrium, the complementary variable is zero, and I'm going to give you examples of that this morning to make very clear what these things are and what something called marginals are in GAMS, which is a very useful thing that is given as part of the solution. Okay, throughout the week, we may look at three underlying solvers in GAMS that takes the program and actually arrives at a solution. Still, I do use optimization some, and I'll show you the relation between optimization and complementarity in a couple minutes. So NLP stands for nonlinear programming, and that's really for optimization problems, constrained optimization problems. So GAMS allows you to put bounds on variables, lower bounds, upper bounds, etc. But you can only maximize one thing. MCP, I don't know who made up this name. I've never liked it, but it stands for mixed complementarity problem. Mixed, I think, refers to just mixtures of inequalities and equations.
If you remove, if the bounds are minus infinity and plus infinity, you have an equation and you have there's no need to associate.
Okay.
Unbound, you need to have an equal number of unbounded variables and equations, and then everything else has to be associated.
Yeah, okay. So these are basically square systems of equations and inequalities and unknowns where inequalities are matched with specific variables, and that matching has to be correct, not arbitrary. And I'll give you an example of this in just a couple of minutes. I don't know that we'll use MPEC. It's a great tool for doing policy analysis. If you have a general equilibrium model and you want to endogenize instruments like tariffs, you can actually use GAMS to solve for the optimal tariff where the constraint set on the optimization is the general equilibrium model. And I've done this in some papers, and it's a really cool tool. Solving for optimal tariffs used to be a brute force search procedure where you have a grid and you find it, then you refine the grid and you run it again. And MPEC can actually find those values of instrument variables directly, with the constraint set being the general equilibrium. I do have an example. Okay, so I'm starting simple. This is a model I actually added. I don't know that I sent you this one, but this just gives you an idea of what a GAMS file looks like. The coloring and changed a little in GAMS Studio, but Studio, I like it for starting out. Tom likes a much more sophisticated programmer's editor, but the neat thing about GAMS Studio is it's a built-in editor. You don't have to go anywhere else. You write the program and you run the program from really within the same window. So this is a very simple example of an optimization problem. Firm maximizes profits, which are revenues minus costs. This is in the notes at the top there. Star at the beginning in the first column indicates a comment and means ignores what comes after. There's one input, which is labor. And so X is L to the alpha, where alpha is between 0 and 1. So you need some concavity in there. Interior solution. P is the price of output, W is the wage of labor. It's a competitive model. The firm takes P and W as given. So the first thing usually in the GAMS program is declaring parameters and sets after you documented what it is. So when you go back 6 months later, you know what you're doing. I frequently had the problem of not documenting my code. Months later, I go, what the hell is this? I just,
Let alone to read someone else's code,
yeah.
right? That's it.
So you can declare a parameter. If there's a space after that, it's treated as a comment. And one way of setting an initial value of a parameter is the slash notation. These things you see in green. That sets initial values of the parameters if you want, or you can, after declaring parameters, you can just say P equals 5 semicolon. Semicolons are at the end of a statement or group of statements. In this case, there's a group of parameter declarations. You have one semicolon at the very end. Then the word variable is a it's the default for unbounded variable. So upper bound is plus infinity, lower bound is minus infinity. In an optimization problem, the objective function variable to be maximized and medium wise must be called a variable, unconstrained variable, or it won't doesn't. Non-negative variables, though, are implicitly setting this, in this case, a lower bound, so that allows you to make corner solutions. So then you declare equations, and the name of equations can't be the same as variables. So profits go to profit word and a first order condition to show the equivalence here in GAMS between nonlinear, between NLP and MCP, between an optimization and a complementary problem. So I have two equations, and the notation in GAMS is the name of the equation dot dot, and then you write the equation, the objective function for optimization here is profit. Notation in GAMS is you have equal sign E, equal sign for inequality. If you just put in equal sign, it's not going to run that. That's used for assignment statements. And then this is revenue minus cost, so price times labor to the alpha minus WL is profits. Semicolon, a lot of errors, you'll make errors over and over again in GAMS by leaving out semicolon. It just continues to try to read the next line. It gets very confused. And then for the alternative way of solving for this solution is to take the first order condition, the derivative on pencil and paper, analytically, of the objective function, and that becomes a weak inequality, the wage is greater than or equal to the marginal product of labor in producing. Just derivative of profit equation with respect to L gives you this formulation, and it's written in this form. If W is strictly greater than the right-hand side in equilibrium, that's a corner solution. It's unprofitable and optimal outcomes. And so you have to write these things in the right direction. So then a thing that we do, and I may have time to show you why this is very important in nonlinear problems, is to set starting values to help the solver get going. Because if the defaults are 0, and if you start with zeros, it may not. I have an example of why that something goes off to minus infinity or plus infinity. The solver just doesn't know. So the notation in GAMS is the name of the variable dot L. L is not fixing a variable, it's just setting its value temporarily until it might be changed later. So at very least, just set these things. Okay, so there's 2 ways of solving this little toy model. One is as an NLP, and this is the notation. Have to give the model a name that you're going to solve. So the keyword is model, and then you give it a name, which is not something used elsewhere. I call the model name profit NLP, and then you have to specify the equations or inequalities that go in the model. In this case, there's only one. So profit is the name of the equation, semicolon. And then the keyword is solve, model name, using nonlinear programming, maximizing profit. Profit is the variable. Profits is the name of the equation. That's notation. We just have to have different names. That's all. It could be Joe.
So one comment here is that one evidence of GAMS being an old program, somebody on the call was saying they used GAMS in the 90s. One way that you can know this old program, it's a not case sensitive. So you can use, lowercase, uppercase, GAMS thinks it's the same thing if you change. However, even though GAMS is not paying attention to it, for your own eyes, it's helpful, although Jim doesn't follow that format here, it's helpful to use sets and parameters in lowercase and variables in uppercase. Because then when you go back to your own code 3 months from now, you look at your code, you can tell, you're reading someone else's code, you can see the uppercase of the variables getting determined by the model. The parameters in the sets are lowercase, and those are not the same. So this is a helpful format.
Yeah, I don't know. I hate reading code in lowercase. Somehow my brain doesn't like it.
Yeah, Fortran programmers have that characteristic, right?
The other issue is that you really want 3 cases.
Yeah.
Because you want a case for comments.
Yeah.
And so I use lowercase for comments, and yes, I think Tom is probably right, but I kind of got marked into this thing. All right, so GAMS solves the model, and we'll show you a listing file later on. But you can also then, after you solve the model, extract and display some information, other calculations from the solution. So I've just shown there, you can have a parameter called PR, which is for profit equals profit dot L. Now, the reason for this is that GAMS for a variable stores 4 different values for a variable. It's lower level, if level, which is the solution value, it's upper level boundary, I should say, and something called a marginal. And I'll tell you in a little while what the marginal is and why it's very, very useful in policy analysis and counterfactuals.
Just to interject here, Jim, if it's okay.
Sure. Yeah.
So the one thing is, I'm thinking about the audience we have here. So Commerce wants to get into having a new tool in your toolbox. That's great. And we like this idea. There are different ways you can go at this. We can put together the perfect model and hand the model to you saying, here's a model that does everything. The problem is that we don't believe that. Our view is you take the problem, you figure out what the question is, you address it. Now, you may be able to find a model which is close to what you want to do, and you'll have to make a few edits. But our view is to become effective as an analyst, you have to become aware of what the framework is. Not that you're going to design a model from scratch every time, but you want to take an existing model and make changes to it to do the thing that you're doing. And at the very minimum thing is, and I don't anticipate that everyone in commerce would have the same level of facility with the framework. Our client here is Colin here. We're trying to help Colin get up the learning curve. He's all in.
Yeah.
So we're trying to help him. And I think Jim's introduction is perfectly designed toward his framework. For people who are in the call who are interested in learning how to use one of Colin's models, this is a point where you really want to pay attention, is that you have a GAMS model, understanding where does the solve take place? How do I get the numbers out of the model? How do I display things to see what's coming back? That's something everyone wants to learn how to do, is how to take an existing model and to make the edits required to interpret what's happening. So along the way, we're going to basically, the beginning here is going to be designed towards someone who wants to learn the whole big picture, like how things work. But we'll also, at different points in the week, we'll also break in and say, okay, here's an existing model. Let's just focus on how to use that model.
Yeah.
And that's a different audience than there's, I recognize people have different interests, but
No, I think this is perfect, by the way. This is like perfect, just line by line, breaking down the code.
it
For
seems,
everybody,
for everyone, I recognize for people who've been out of school for 10 years, this may seem like a big, we're back in school, but the fact is that that's sort of what's required to get this stuff together. It's like, yeah, it's kind of have to begin. It's Zen mind, beginner's mind.
Okay, well,
Yeah.
good, thanks, Colin. I'm glad I'm kind of on track, because I didn't, we kind of go through this, I think, really quickly, but if you start in the middle, I mean, sometimes people just get lost.
Yeah.
and realize.
Yeah.
Okay, thanks, both Tom and Colin. Please interrupt with questions. So,
Just one question. So we
Sure.
said there are 4 solutions for each variable.
not solutions.
Not
There's one
solution.
solution, but it displays 4 different values.
Values, okay.
You'll see this in.
So go to the previous page though, Jim. So if you think about how GAMS works. Part of GAMS, it's got a declarative structure built within a procedural structure. So this seems like an abstract computer sciencey sort of concept, but it's very relevant. Declarative structure, profits, ... That says there's nothing going on there procedurally. That's just a declaration that says, I'm going to declare something called equation profits.
Mhm.
And that profits relates, it has a relationship between variables and parameters in the model.
Right.
It says that thing, that's an equation that relates profit to this other stuff. And that way, the variables we've declared, profit, is something that's a concept of a symbol. And there's no number associated with that. That's just an algebraic relationship. We go to the next page, Jim. The procedural statement that we have that relates to that declarative model is the thing that says solve. It says solve says, take the parameters I've given you, start from the starting point I've given you for the values, go out and solve that model. And in this case, solve means using NLP, solve profit NLP, using NLP, maximizing profit. So find the value of the variables which maximizes profit. At that point, we've solved the model and we say, okay, we want to get back the solution. We want to know what the numbers were. And that's where the .L comes in. L.L tells you for that abstract model, what's the value of L which maximize things. There are 3 other numbers related to L. 2 of them are bounds, which we've relied on the default bounds here. We say the default bound, lower bound is 0, the default upper bound is infinity. And there's something else called the marginal, which is going to be it's the Lagrangian associated with the bounds. So those are other numbers, but most of the time you're solving them all and you say, what is the solution?
Right.
And in that case, that means you have, in GAMS, there's a very standard sort of set of equations that says solve, operate on my database, load the solutions, and then assign the values of the level values so I can see what came back. Okay, so that's
perfect. Yeah.
so that's, so it's this procedural, and the best analog for people who are in sort of business or government work is Excel is both procedural and declarative. In an Excel sheet, you say A1 is equal to A10 times 20 plus F25. That's the declarative structure in the model.
Mhm.
And then in Excel, you can write a little macro that does things in sequence. And that's a procedural thing. So Excel tends to be largely declarative with a little bit of procedural.
Mhm.
GAMS tend to be an equal mix of declarative structures, which are the models, and procedural structures, which is the sequence of operations.
No, that's
Okay, yeah,
perfect, yeah. Is that good for you? Think?
Yep.
Okay.
thank you.
And hopefully, that GAMS is also a scripting language, so hopefully you'll catch on. It's intended to be such that you get a few ideas and you can guess what the rules are. Because you just get a sense about how this works and then you can guess. But it takes some time to get to that point.
Great, okay. So I was on this places. Okay. We'll look at the listing file for GAMS, but if you want to extract added information, is what this little bit of code here is in the center of the slide. You can have a parameter declared called PR, set that equal to profit.L. GAMS has to know which of those four values you want from that variable. Labor L.L. Output is just the production function, and then there's so many parameters often in big GAMS models that it doesn't automatically put them out. So you have to actually say display, and then list the parameters separated by commas, semicolon at the end as follows. So then at the bottom of the slide is the other way of doing the model, just to emphasize the equivalence of these things. So it's an MCP at the bottom. And again, this is just an unconstrained single equation optimization, single equation model. So here you say model profit MCP. That's again, these model names are completely arbitrary. You can name them after your cat or, actually some politician, as long as you do it consistently. You have to have the same thing. So I call this profit MCP / there's only one equation, but in an MCP, right, it's this inequality formulation from the KKT condition. So you have to say which inequality is associated with which variable. Here, there's only one of each, but you've got to have it in there. So you say dot L, which is a variable. I'm sorry that's confused with level.
Yeah, no,
It's
but
not
that's
the
okay.
best notation. So here the dot L is not level, it's labor.
It's equation dot variable, and you have a variable called L.
Equation.
Yeah.
Sorry about this, was not the best choice. So then you display those again, and I'm not going to try to go back and forth here just yet between the actual code and run it and show you that these are the same. So this is one of those trust me statements.
That's the second.
You're going to get the
So
same.
do you need the display at the bottom of that one, or will it just display on
No.
its own? You don't need it?
Next line, I think, Jim.
Yeah,
Oh, it's
sorry,
up there.
my
Okay,
apologies.
sorry, I just got confused.
Okay, and then counterfactuals in GAMS, if you want to start playing with the model, you will change some parameter. You put in extra parameters like to change the technology, but they have to be declared as parameters. So here, just as one example of a counterfactual, what if the price doubles? So you say P equals 4 semicolon, and then you can solve both of those models. And again, make sure they better be the same, or
So it's very similar for people who've used GEMPACK. It's very similar to GEMPACK. GEMPACK's the same idea, although in GEMPACK, the typical GEMPACK user tends to rely much more heavily on using someone else's model. So the standard approach to GEMPACK is there's one model, we have the model, we just want to learn how to run that. You can use GAMS that way too, but GAMS tends to be used more by people who are interested in the question of how do different models work? How does the model of assumptions affect the results? So they want to be able to manipulate the structure, and GAMS is really very facile with that. Of course, the other thing Jim emphasized here is complementarity is something you can do in Genpact, but it's not sort of automatically included, whereas here, it basically, this is part of the framework. So,
Very awkward.
Yeah.
Oh, sorry, I'm just reviewing. Okay, so this next model, and I'll make sure that you can have access to these. I added these over the weekend. And this is just a small extension of that one where we have constrained optimization. So this model is going to minimizes cost of producing 1 unit of output from labor and capital. So there's 2 inputs. The technology is Cobb Douglas. X is L to the alpha, K to the 1 minus alpha, where alpha is between 0 and 1. And X will be set equal to 1 when we solve for the minimum unit cost of producing 1 unit. W is the price of labor, R is the price of capital. It's a competitive model again, so the firm takes W and R as exogenous, so they're declared parameters. And so if you were to give this problem to a first-year graduate student, the first thing they would do is probably write it down as a Lagrangian function. Everyone knows that terminology. So you'd write down minimize WL plus RK plus lambda, the Lagrangian multiplier introduced, 1 minus the production function there, ending in the semicolon. So this little extension of the first model has a couple more parameters. Well, it has the alpha parameter we had before. Price of labor and capital are exogenous, so they're set at 1 each. And then 3 parameters for extracting information from the solution after the solve state. Minimum cost, labor, and capital levels. So again, if it's going to be an optimization problem, you use the word variable, so it has no bounds on it, which is required by the NLP solver. So we say cost variable to be minimized. Non-negative variables are labor, capital, and lambda, Lagrangian multiplier, these, normally we think of these Lagrangian multipliers as a pain in the butt. They actually have a lot of economic information.
Shadow
Sometimes. And I will show you this in the next example that's coming after this. They're shadow values of things. So in policy analysis, they're important. It says how unprofitable is something in equilibrium. Okay, so then there's 2 equations, cost and technology. Cost is the objective function to be minimized. That says maximized, it should say minimized, but it's not, it's just a comment statement, so it doesn't matter. I love errors that don't matter. It's often said about Paul Samuelson that he made lots of errors, but they never matter. I believe the first part, I'm not sure.
So one thing to just in terms of GAMS syntax, I love Jim's introduction because he teaches you GAMS syntax when you're not really thinking about it. He's talking more about so it's great. But here, if you're not paying attention, you may not notice these things. It's like the color coding gives it away. The percent, the star sign in the first column represents a comment.
Yeah.
There's a title at
Must be
the
in the first.
must be in the first column.
Yeah.
There's a dollar title at the top that gives a name for what the model is you're running. That gets echo printed in the listing file on every page. He gives names to the parameters followed by, and this is this free format of the layout of the parameter. It's just got the name, the description is expected after it. And then if you want to give a value to the parameter, you put a slash and then the number. and then a slash. You can put a
Technically, you don't have to have any of the blue though, to the right.
That's right. You could
You
skip
could
that.
That's correct.
Okay, you could, but you would need those values. What if you didn't put those values in? The
Then
0.5?
notice the min cost, labor and capital have no values.
Yeah.
So they're not assigned. They're just going to be used below. You'll make an assignment. Those will be assigned.
Okay.
So typically, parameters that will contain data that are coming in from outside, and there'll be other parameters which are assigned
Mhm.
parameters. So there are things that are, you can declare a parameter and then give it a value by making an assignment statement.
I
So
see.
procedurally,
That's what's, okay.
So you don't, the other way of doing it, rather than the slash notation, is after the semicolon at the end, you can have a line that says alpha equals 0.5 semicolon.
Sounds okay.
That's the equivalent.
So you would write it
I often
again.
do it that way, so I know exactly where to look. for it.
And that's because of Cobb Douglas.
you're gonna, the value share is gonna be relevant for any type of CES function or any
Yeah, I
sort
guess
of
this just
calibrated
says
function,
constant
but
returns to scale.
Yeah.
in the Cobb Douglas, that's the only parameter we need for
Yeah.
the function, right?
Has to be between 0
One, yeah.
otherwise you curvature goes wrong.
Yeah, the-
Second order conditions are not satisfied.
And then the thing is the variable statement and the non-negative variable statement. The variable statement is something to declare a variable that has no, the lower bound is automatically minus infinity and the upper bound is plus infinity. Non-negative variables, lower bound is zero, upper bound is infinity.
infinity. Okay, yeah.
Right.
You'll see that in the next example. How to do one thing.
Well, this is good. This is good.
Okay, so cost and technology. Oh, by the way, one more thing about parameters and equations. If that alpha there in the first parameter thing, if you have a comma after it, it means that the next thing that comes along is also being called a parameter.
Yeah,
So the blue would disappear on the word share. And you would have declared a parameter called share.
yeah.
Oh,
So if you want to have a list of parameters on one line, you use commas. But if you want them to be comments on the first thing.
just leave it.
It's both a strength and a weakness. So a scripting language should be forgiving. It should let you write however you want to and ignore rules. They typical, rules are like C++ and C and Fortran are all have very strict rules. Here it's like, oh, you want to put a comma at the end of the line? Fine, go ahead.
Yeah.
If you don't want to use the comma, that's okay too. So it's not structured. It's not unique, it permits you, particularly the comma is something you don't have to have it at the end of the line. It assumes if you go to another line, GAMS says, okay, you forgot the comma, no worries. I'll just assume that's a parameter.
Hold 1 second. I think we have a question in the chat because I saw that move from 6 to 7 at some point. I just want to make sure we're addressing
Yeah.
the questions. Do we have a question, Martha?
You need the display lines again to see changes, right?
Martin, do you just want to pop on and ask the question?
Yeah.
Maybe we need to go back a slide or.
Martin Johnson.
Yeah, I think Martin asked the question.
Yeah, you have to display if you wanted to see, although there will be, the thing is, we'll see when we look at the listing file here, that there will be a solver listing given. So we can look at, GAMS will give you at the end of the solve, if you don't tell it not to, it will automatically give you a list of all the variables. So you'll see the variables and all the Lagrange multipliers and everything in the solution. But then if you want to have a format things to look at it a particular way, declare a parameter, assign it, and display it. And that's part of the skill for people getting started. If you're just trying to help out someone who's an expected, suppose that Colin develops a cool model of FDI and it's running and he wants to have somebody help him understand what happens over the parameter space. He shares the model with you. You're still going to probably want to learn enough GAMS that you know how to make assignments and look at solution values. So there's this process of taking an existing model and learning how to add stuff to it to better see what's coming out. That's a set of skills that's very valuable in addition to the skills of what's the right model, right? So there's different skills. Okay, so this is good. Jim's going through. So now we're going to go back to a model that's a little more complicated with 2 equations rather than just 1.
Start
I
from the
have
bottom.
one paper that's 36,000 equations. All done in 3-dimensional sets. And the
Yeah.
code fits on like 2 pages. Small steps, baby steps. All right, so declaring 2 equations, cost and technology. Cost is just an equation, W The technology, which is the production function. And then if we're going to treat this as an MCP, there's two first order conditions, one for each of the two for labor and capital. So here's 4 equations. And again, you can have extra equations. A model declaration may only use a couple of them. So just write them all down. And as you'll see below,
You can mix and match.
you can mix and match. Yeah. So cost is just, oh, yes, also if you're optimizing using the NLP optimization solver, you can't use G because something will go off to infinity. You have to say equals. Equal sign E equals for the objective function. So that's just cost. The technology that's constraining our cost is the production function. Cobb-Evans production function has to be greater than or equal to 1. You're minimizing costs, so it's going to be push down to 1. And then from that Lagrangian equation that I wrote at the top of the program, you take the partial derivatives with respect to W and R, and this is the two then first order conditions, one for labor and one for capital. I think that's pretty standard stuff.
But again, this is where GAMS departs from GEMPAC. So in GEMPAC, it's all log linearized. You express things as you don't write the nonlinear system down. The levels model typically in GEMPAC usually rely on just writing the first order conditions. Here, GAMS is strictly write the equation down. If it's nonlinear, that's fine. We handle the nonlinearities. So that's the key strength you get here. And this is the relevance of GAMS, why GAMS is as old as your grandmother, but still is actually useful, is that if you look at existing software, there's only one open source tool now which can solve this class of problems called Julia Jump, but it's written by a couple of MIT math professors, and it's actually hard to use. It's not so easy. So GAMS continues to be the dominant tool for just write down the nonlinear equations, solve them. GAMS is basically the package. You can't do this in R. R can solve certain linear problems it can solve well. You can do it in GEMPAC, but it's not really set up for solving levels values. And there's really not a package in, well, there are packages for solving nonlinear models in Python, but they're not very easy to use and they're not general purpose. So this is basically the only game in town for doing this large scale.
Okay, so again, I formulate just to show the equivalence. Comfortable with this. There's 2 ways of solving this model. One is an NLP and one is an MCP. So model declaration, model, the name I've given is cost NLP. There's 2 equations. They do not have this dot notation in the NLP solver. So these, there's many ways to get confused along the way. So the 2 equations are cost and technology, and then solve cost NLP using nonlinear programming, minimizing cost. And we'll show you what a listing file looks like in a minute. And then after you're finished, you can extract things into parameters, make tables, stuff that we'll talk about as the week goes by. Again, if you want the variable, get something from a variable, you need this .l notation to tell GAMS which of the 4 values stored for the variable you want. And typically, it's the L, the level value, the solution value. And then you can say display. The other way to do it is as an MCP. So that uses the first order conditions. Here we want to solve 3 weak inequalities and 3 unknowns. So the first order condition for labor, .L, first order condition for capital, .K, and technology, which is the complementary variable is is lambda.
This is gonna be a basic question, right?
Sure.
So if you delete your equations up there, FOCL and FOCK, and delete those.
Yeah.
Could you still run that NLP model?
Yes,
Oh, yeah, yeah,
So
yeah,
you don't even need, okay, so you're just putting those in so you can show both ways. So
right.
you can do it one way where you have the first two, cost and technology, you can run it NLP. Or you can just, you could delete cost and technology and just have the first order conditions and run the MCP. Or do you need cost and technology in there for that too, because you have technology lambda? Basically, for the
Yeah,
MCP,
no.
let me rephrase, what of those four do you need?
Well, okay, so the model declaration tells which of the equations you're using,
Yeah,
and it just ignores the other ones.
okay,
Okay, so the NLP is cost and technology.
so that's where you don't need the first orders. Okay,
Now,
using the MCP, you
on the
need,
MCP, you actually do need three equations, because if you just have the two first order conditions, those are homogeneous of degree one in
Yeah.
all those three variables. That's not right. W and R are parameters. No, but they are. You need the technology equation to
well, to solve for lambda, right? No,
yeah. Right.
but then I guess we.
Yeah, otherwise there's infinitely many solutions. to
Yeah.
the two first order conditions that all have different outcomes.
Anyway, I
Yeah.
was just thinking on that, and I just trying to
No, you can
understand what
have-
attaches to what.
Right.
Because you
So
could simplify some
the
of the
model
code.
declaration, the NLP model declaration just says we're just going to use two of those.
I see, yeah,
So that's fine.
yeah, and then you don't even need to work out what the FOCs are.
Yes, but as soon as the world gets, there's two different agents optimizing different things, the NLP thing falls apart
Apart
very
quickly. Okay, that makes sense.
that's the essential point.
Yeah,
I mean, the
yeah,
point is you
okay.
want to solve a model where you have. And this is an important thing. It's important to say that we're not asserting that everyone is a perfect optimizer. It's just that this turns out to be the simplest assumption for closing a model, is assume that they optimize something.
Okay,
And so if you want to write a model down with multiple agents where optimizations describing their behavior, you have to write down the first order conditions to get them to work together.
nope, that's good to know.
So that's essentially what we're doing. We're learning how to.
That's perfect. This is, I know some of these are basic, but I think this is helping, at least the feedback.
Yeah, no, that's good.
Okay,
I had, most of what I'm doing for you is stuff that I self-taught myself. So what I show you in 5 minutes might have taken me several hours. I'm trying to save your lives. Okay, so then extract things, and again, the way you do a counterfactual is just change the parameter value. And you don't have to respecify the model, it's the same model, you just need the solve state. Right, so solve it both ways, and you want to check that they're both the same answers. If you want a second counterfactual, remember if you to set W back to its initial value, if that's what you want, it will retain any parameter changes in subsequent solve statements. So if instead you want to change R but not W, you've got to change W back. I think we can get through this, and then it will be, we'll have a good stop. Okay. This has
I just
The
sent you some
feature,
PDF files from one to
GAMS
talk and a couple papers.
that
So I said,
basically changed my life. So my multinational book, making use of this, of complementarity to solve models where you have regimes shifting all over the place. Am I going to serve the foreign market by exports, or am I going to plant and produce locally? All those kinds of things. So this is a model of supply and demand in a single market. There's two equations, supply and demand, two variables, price and quantity. So now we're going to first year undergraduate economics in some ways, but with very important generalizations. So an economic equilibrium problem is represented as a system of equations with matching modes or inequalities, I should say. So here we're going to have a supply of a good X with price P. The supply curve exploits the firm's optimization decision. So we build optimization in rather than saying optimize. So for first year undergraduates, we were taught that marginal cost equals price is the optimization condition. Here it's a little more complicated. You'll see why. We want to say marginal cost is greater than or equal to P with a complementary condition that X is greater than. It may be, so in a model with a number of technologies, you may only use one of them, the most efficient one. And other ones will, in equilibrium, have marginal cost strictly greater than price. So you don't want to use that. So that technology, the output from that technology is zero. So it's marginal cost greater than or equal to price. Marginal cost can be greater than price, but if price is greater than marginal cost, somebody's not optimized.
Or so in the FDI setting, there are lots of situations where this sort of logic would seemingly apply. There may be technologies, there's production processes which are currently in the use in the US. There's not the option to move this offshore is not there because of the lack of public inputs, infrastructure, roads, transportation systems. It may be the lack of a well-developed labor market. There may be restrictions on foreign investment that were presented. If you make a change where you assume that suddenly things are going to change and the production process can be fragmented and there can be a movement, then it's essentially you're into this world where you're trying to predict where something is going to take place. Where is the manufacturing going to happen? And that's so the framework gives you the ability to posit the existence of the emergence of technologies which are not available, and then you can model what the consequences are of that output. Now, of course, the framework is not going to tell you what the right assumptions are about how to represent these things. How are these perfect substitutes or not, or the variety of other factors that play. But the thing is that you can do thought experiments, and Jim is very good at this. He'll show you ways that you can illustrate that. But this model is just capturing this idea that, hey, we can model things where the user example I like for students is to say, when I walk home in the summer from here to my house, lots of opportunities for buying lemonade because little kids are having lemonade stands out on a hot day. When I walk home today, I'm not going to have the opportunity to buy lemonade. That's a technology that exists, but it's not profitable, so nobody's operating it, so we don't observe it, right? So this idea that there are these things around that could exist, and they when they become profitable, then suddenly it'll pop in, and that's where you want to model what happens when this comes in. How much will it come in? What will happen?
Frozen lemonades. They could just leave out the lemonades and you could have frozen lemonade.
Exactly.
Okay. So here's our first inequality. So here's a specific functional form. Cost is quadratic, so there's increasing marginal cost. So marginal cost, just take the first order and what's the derivative of cost? Output. You get marginal cost is A plus Px. So the inequality becomes A plus Bx greater than or equal to P complementary with X greater than. So then on the demand side of the market, there's also an optimization problem. You can see why you can't just treat this as a single optimization problem. So the consumer maximizes utility for given income prices, and that yields a demand function of the form X is a function of P and M, where M is income. So there the inequality is going to be X greater than or equal to demand with a complementary condition that P is greater than or equal to 0. Why is it written that way? Well, in equilibrium, it may be that supply is so large that it exceeds demand even at a price of zero. Now, well, I'll give you an example of this, like pollution permits, just about 2 minutes. Okay. Demand can't be greater than X because that somebody's not optimized. So the inequality goes X, supply is greater than or equal to demand. The supply is so big that there's excess demand even at a price of zero, and the price is zero. We don't run into a lot of examples of this, but there's certainly some. As I say, you could have supply of pollution permits, which is so large that the market clearing price is zero. So the quantity equation is complementary to price. Okay, I'm going to suppress income in the back. I'm not going to change income. So we just have a demand function. I'm going to assume linear. C is the intercept on the price axis, and minus dp, where C and D are both positive parameters. So the equation, the inequality becomes X is greater than C minus dp, complementary equals zero. So you do in MCP, you have to be careful about which inequality is associated with which variable. That comes from theory. Hey, if marginal cost is greater than price, then you don't want to use that. That must mean the X variable is equal. And for demand greater than or equal to supply, if there's just so much supply out there, something's going to be zero. It's going to be the price. Okay, so this simple supply and demand model from first year principles of economics undergraduate, they don't tell you this, but there's actually 3 valid economic solutions to the model. The one in the upper left is the one from the principles of economics textbook, right? There's an interior solution where the supply and demand curves cross. That determines price and quantity. And in this case, you really don't need complementary. The bad news is some other software forces you to, this is the only thing that you're allowed to compute. Because it's not, it doesn't have solvers derived from economic theory that permit the other 2 possibilities. Right, so the next solution on the upper right is something that happens in big, should be allowed to happen anyway in big models all the time. It's where the supply curve everywhere lies above the demand. They cross somewhere over in negative X, but that's not, we're not allowing that. We're bounding X variable to be non-negative price. So the solution to this model is that X equals 0, the complementary variable. Marginal cost is strictly greater than price in equilibrium. And so the output is 0. So there's many instances in, say, trade models. This could be representing a trade link, the export of good I from country to A. This flat is 0. And the real world trade matrix is full of zeros. And often people impose like the Arlington assumption of national product differentiation, which does not permit those things to happen. I mean, CES demand will always be some little trade on every possible trade link, every possible.
Yeah, that's right.
So this is important when you want to allow for these regime shifting. Something becomes active or something becomes inactive, or you could even have some measure that reverses the direction of trade, some subset.
But the thing is, if you think about the example in the upper right, one of the things about this framework, it doesn't solve all the problems for you. You still have there are modeling issues that you hadn't anticipated. If you're working in a Armington world, everything is calibrated. You just have one or two elasticities, demand and supply, the slopes of the curves. Suddenly, if you go into this other world where you have differentiated goods, which are or non-differentiated goods, the problem is when the supply curve shifts down, you have to describe at what price does the demand curve become positive and what is the slope of that curve. You don't get to observe what the slope is from observations of price and quantity. So there's this thing about understanding what happens when a link becomes profitable. You're in a world that's more complicated because you have to worry about what's the price at which it shifts in and what's the slope at which it takes place.
Yeah, that's a good point. So we don't. The thing is, things that are inactive are not observed, and so you might not know what that price is. So this little distance shown on the upper right diagram labeled S1, that's really the slack variable, and I'll show you that. But you have to specify what that alternative technology is. You may not know that, but engineering, like different forms of electrical generation. So you have your coal-fired power plant, you have wind, you have solar, and some of those may be unprofitable at current prices. The question is how unprofitable? Well, in this case, they're actually engineering data to tell you what that S1 is.
That's the standard. It's really the standard approach for linear programming. It's this idea we have a bunch of technologies on the shelf. Many of them may be non-profitable. We're doing the model to identify which one. So it's a different set of issues, but this accommodates the idea that the world may be described by economic data or by engineering data. We can combine both of them. The one comment I'd make, Jim, about these three examples is that in my undergraduate class, if you can solve the upper left one, you get a B. If you can solve the upper right one, you get a B plus. And if you can solve the bottom one, you get an A, right? So it's very easy to give students see the Marshallian model, they think, oh yeah, I know exactly the solution. And you give them ones where suddenly the guys don't intersect, then suddenly it becomes much more challenging. But all three of them are perfectly legitimate
In your
circumstances.
undergrad?
Yeah.
No, but see, he went to Yale. There is no mark below B. So that's why you get a B for the upper left one.
Yeah, right.
Gentleman C was eliminated in that.
Yeah, that's right.
Okay. All right, so the third case is something that we don't run into as much, but there are cases, and I gave you an example of each of the Berlin. So the third case is where the demand curve, consumers get saturated. You don't want any more of this stuff, even if it's free. So the supply curve lies everywhere to the right of the demand curve. Again, we're constrained. They cross somewhere at a negative P. There might be cases where you want to model, getting rid of pollutants or something, but it could happen. But basically, again, we set P as a non-negative variable. So the solution to this third case is that the price is zero and the demand is the saturation, is the stuff. And I guess there's a free disposal function. So S2 here labels the difference between supply and demand at a price of zero, and that's going to be the marginal in GAMS as it's S1, and I'll show you that like in the next slide. So cases like this aren't too normal, but I frequently think of those European emissions permits for power plants. It got to the point where the price was essentially zero. There was some positive price because some speculators were just buying them in hopes that someday that they would become valuable. So there are a few cases of examples like that. And pollution permits, the supply curve would presumably be vertical, right? But it's to the right of the demand. So the solution is a zero price. Okay, So maybe I'll skip this slide. Yeah, so from the Karush Kuntak, I'll just make a comment, but I don't think this is fundamental to what we want to do. Yeah, I want to move on. Karush Kuntak theorem actually adds slack variables to the inequalities to make them equalities. Right, so marginal cost greater than or equal price becomes marginal cost minus price minus a slack variable S1 equals 0. So the solution is if marginal cost equals price, the slack variable is 0. If marginal cost is strictly greater than price, in equilibrium, S variable is positive. S1 times S. And the same thing for the supply and demand. So that's kind of the underlying Kuhn-Tucker framework converts these weak inequalities to equalities for the solver using these added variables. And you don't have to put them, puts them in by itself. Okay. Now, I wanted to make a brief comment about my starting values. Yes. Okay. So this is my. It took me far longer to make this slide. But it illustrates a couple of things that you have to remember when you just write down something and say solve the model. This is my simple version of what's called a Newton method, and it's an iterative approach to solving a nonlinear equation. Okay, so suppose our nonlinear equation is excess supply, and we want to find the zero of that function. So we want to find the price at which supply minus demand equals 0. So suppose the true curve looks like this E of P function. Prices on the horizontal axis here. That's the variable we're going to try to find the solution to. And we're looking for the zero of this function where it crosses E of P equals 0. We don't know where that is. So basically what a Newton method does is make a guess. We call that first guess P0. And then it goes up, then from P0, it computes E of P0. So it goes up the curve. I can use my curve. So you go up the curve here, and you note this value, and you also compute the slope at that price. What is the slope of E prime of E? E prime of P is the slope. And then there's an iteration rule that says your next guess is going to be given by this formula. You're going to follow that tangent line down to a new value of P, which is here. Look at that intersection. And then you repeat the process. Your second guess, that becomes your next value. You compute E of P as the slope. And you keep doing this. And if this thing is well behaved, this iteration will converge to the solution you're looking for. And this generalizes to n equations and n unknowns. This iteration rule, the new vector is the old vector minus the inverse of the Jacobian of the system times E of T. So you can do this with 1,000 equations.
One thing about this comment about this is useful. It seems kind of abstract, but actually it's kind of useful when you watch your model solving in GAMS. And we'll be doing more. So you're watching it solve. There's a piece of theory from here that helps you know something, because when you write down a model, there's always this challenge to know how tightly can I compute a solution in this model, and that's a question about have you scaled the model properly. If you scale the model to dollars, then you've got numbers in the trillions floating around. You can't get a precision tolerance of, you're going to be off by, you can't get something down to 10 to minus 6. If you've got 10 to the 12th, you don't have enough degrees of freedom. The computer is only keeping around 8 digits of precision around. So what this tells us, the theory of the Newton method tells us that in the tail, that's as you get close, it's going to converge by an order of magnitude at every step. So if you watch your model, when you first get started, you can observe how quickly it converges. And if you see it take a couple of steps where it converges by a factor of 10 or 100, you know you're at the solution. And if it doesn't solve at that point, it means you don't have enough precision to solve it. You've got something scaled wrong. So this theory is helpful even in practice to know a little bit about. And it also explains why if you give it bad starting points, you're screwed, right?
I'm gonna do that. Now.
Okay.
Okay, so there's two practical things for model. First of all, this isn't gonna work. This function E of P, excess supply, has to be differential. It's not gonna work if you know there's kinks or other software. Secondly, note what happens if you don't get a starting value. So the default is 0. Well, E of P is minus infinity, which so if the price is 0, maybe supply is 0, but demand goes off to infinity. Maybe there is no saturation. That would be true with the Cobb-Douglas utility function. Stuff. So it can evaluate E of P, and it certainly can evaluate E prime of P. So starting value is very important getting this going. The GAMS solve is pretty good. If you have minus, you'll nudge that variable a little bit and try again. But basically, you're asking for trouble in a nonlinear problem if you don't get some kind of stuff. 1 is a lot different from 0.
Yeah.
You can evaluate E of P, and you can evaluate E prime. Okay. So, and also GAMS then can compute a corner solution. So maybe corner solution here is going to be excess supply. So the price is 0. That was my case 3. Right. And then this vertical thing, distance labeled S, is going to be the marginal in the solution, which I'm going to show you what that looks like. So GAMS has no trouble computing a corner solution. Sorry, I'm just seeing where I'm going here. I think we can get close to ending at 11:30. Be a good time. Right.
Yeah, it's good. That's right.
Okay, so let me just go through this, and then maybe after break we'll actually run a couple of these models. This model has 4 parameters, A, B, C, and D, which are these supply and demand parameters. They have to be assigned values. So, Colin, this is the other way. Instead of the slash notation, you can just use equal sign.
There, yeah, I see.
So
There's a slash too.
remember in computer code, for those of you who never had the pain of going through Fortran back, decades ago, that equals in computer code actually means assign. So you can have an equation that says A equals A plus 1. Now in math, that's not, that makes no sense. But in computer code, it makes complete sense. It says take the current value of A in memory and add 1 to it to get the new value. So equal sign really means assign. Assign to that parameter. So 2 non-negative values, price and quantity, 2 equations, supply and demand. Notation for specifying those equations in our supply ... A plus BX, that's marginal cost greater than or equal to price. Demand ... X greater than or equal to C plus DP, so supply greater than or equal to demand. Then the keyword model, I just called it equal. 20 years ago, I think you could only use 7 characters.
Yeah, that's right.
So model, MCP problem, so you need the dot notation. So the equations are supply dot X, comma. I don't think you need the comma anymore, actually. Demand dot P slash semicolon. Solve equal using MCP. Okay, and then counterfactuals are set A, the intercept of the supply curve and a larger value. Yeah, A was 2. So now the supply curve will lie everywhere above the demand curve in the positive area. Or further on. Case 3, do the opposite, set A at -7, and now the supply curve in the positive orthont will be everywhere to the right of the demand curve. This is how to compute those. Okay, let me just, rather than read this, just go. So if you run the model in the listing file, the .lst file, you'll see the following. Okay, so maybe I should have done this earlier when I talked about the 4 values that are stored by GAMS. So now you go down the listing file, you see where variables are, and this is what you'll see. For each variable, there's 4 columns. Lower level of the variable, the dot means 0. So you declared it as a non-negative value. So it's just setting the default lower value at 0. And the level, which is the solution value. And then the upper value is plus infinity, which also is by default by simply calling it a non-negative value. And then the marginal is the 0 here. It's going to be, well, let me go to the next slide and tell you exactly what the margin is. So in case 2, this is what the solution looks like. Okay, price is 7, but the output is is 0. The technology is not used. The marginal is positive, indicating that marginal cost is greater. So what is this marginal in the model? Well, it's exactly this S value. Okay, it's marginal cost minus price at the solution. So S1 has information. It is telling you how unprofitable that technology is at the solution. And again, you know, that could be hard to figure out if you're calibrating a model where some things are 0 initially. This was Tom's comment. How do we know what that, you know, what that is without some sort of information on things we can't actually observe?
That's the challenge.
So,
I mean, it's an econometric exercise. It's some sort of latent
yeah.
profitability you're trying to estimate. So there are
Well,
techniques,
for
there are
something
empirical methods for dealing with this.
Electrical generation, you can actually get those numbers. The engineers can do those numbers. So note here that, again, the complementary relation, if the level is positive, the marginal is 0. If the level is 0, the marginal is positive. I mean, there could be a knife edge case where, but if you have a level value that's positive and the marginal is positive, you have not computed the solution. Something is wrong. Case 3 was where the supply curve is way out there. So the solution to that model is that X is positive, but P is 0. And so P gets a marginal, just happens to be 1, but that's not an indicator variable 1. That's a numerical value. And so that is this distance right there. This is the supply minus the left-hand side of the equation minus the right hand at a price of 0. That is the marginal value. So, you know, that would tell you in this pollution permit, it says, well, how many pollution permits do I have to destroy in order for the price to go positive?
Yeah.
So sometimes these marginals in, for policy and other questions are really useful. See how unprofitable something is, or how much excess supply we would have to soak up in order to get the price to go positive.
Good.
Yeah.
The key thing is it captures, the beauty of this is it captures the essential idea of what is complementarity about. This gets the key idea. And then the challenge then is seeing the different ways in this can pop up in practice. So we'll see the multinationals application and certainly in the climate policy domain, this happens all the time.
Okay. Just file this away. This will take 1 minute, and I promise you the break. This is an example of the use of MPEC, mathematical program with equilibrium constraints. So here, suppose that what we want to do, we're a government that wants to maximize its tax revenue, doesn't care about anything else. So
Leviathan.
Hmm?
Leviathan
Leviathan.
model, right?
So here I've added a variable, not a parameter, called tax, the tax rate. Tax revenue is marginal cost times tax rate times the output level. So the tax is on the net, it's on the input. So there's an objective function, tax revenue equals, we're going to optimize, so we need equal sign, A plus BX, that's marginal cost, times the tax rate, times the output level, and there's an equation also for supply. Sorry, yeah. Which has the tax rate in it. It's like the other supply. I had to modify the other supply equation. You have to give it a new name.
Yeah.
And so I called it supply 2. So this is a model with 3 equations. The objective function, supply 2 dot x and demand dot p. I don't have to re-specify those from the upper program what the demand equation is. And I can say solve T revenue using MCP maximizing T rev. Right? And so T is, we call that an instrument variable. What do we call that?
Yeah, I'd say it's an instrument.
Yeah, we can call it. That's not a formal GAMS. That's just, I'm going to call that an instrument variable. So we're actually solving for an optimal hash, which is not something that was very easy to do traditionally. Do some kind of grid search.
But it's more, it's in addition to the interest of this inherent example, he's taken an equilibrium model and saying, hey, look, we can look at this from a different perspective. We can say optimize. But it's more this idea that, again, this is trying to sell this idea that learning a modeling language that's flexible like this has lots of advantages because you can take a theoretical concept and you can do a specific example of it to understand, to play with the model. And that's the key thing about Jim's paper about, you know, the third way of doing economics is this idea. We think about abstract concepts and we can actually do concrete examples of them to help us understand what's going on. And it's very, that part of it is, boy, if I didn't have GAMS to use to train out my ideas and see what makes sense, I would have lots of ideas that didn't hold water, right? So this is a way that you can look at it. And this is an interesting question. It's like, what's the tax rate that maximizes revenue at this point? This is an interesting sort of application, but it's one of many ways in which the tool could be used.
If you gave this to an undergraduate, they would get an A++ if they could solve it.
Yeah, this is a hard one.
You know, longhand.
This example does not illustrate the big challenge of MPEC, is where you're optimizing and you don't know what's going to get turned on. You don't know which activity is going to come in. And so that's what makes MPECs different from ordinary nonlinear programs. This one, I think you could probably solve as a nonlinear program. If you constrained it to be within the domain, you could just say solve using NLP. But what gets MPEC gets hard is where you don't know which one's going to be in and you're trying to keep track of the multiple regimes. That's what makes it hard.
Okay, well, anyway, there's the solution to the model, the optimal tax rate is 667, it's 2/3.
It happens to be the German income tax rate.
Oh, it's smaller than that.
So, by the way, in a column epsilon, EPS is epsilon, which is, math for a very, very small number. It's less than 1 to the minus 8.
Yeah,
It's just a rounding error. The solver is stopped. It's within the solver's tolerance. So sometimes you can get marginals that are, 4.673 times e to the minus 8. You ignore that. That's just, it's kind of a residual rounding error for that particular.
good.
Let's take a break.
That's great. Yeah, let's take a break.
So-
So,
Online,
Any
what time do we wanna-
questions?
yeah, maybe you should let people ask questions about,
Oh.
are there specific general
Yeah,
things?
sure.
Questions, and then let's just try
Frank?
and map out like
Yeah.
what's gonna happen for the rest. of the
What's
day.
happening the rest of the day?
Yeah.
So we want to let people know what we got.
Natalie,
Which one?
does anybody have any questions on there, or Martha?
I don't see any on the chat, but I mean, does anyone have any questions they want to bring up right now? All right, I'll go with no.
It's great.
Okay.
So take a break for, I don't know what we have in mind. So Jim, your idea is to move on to multinationals is the next direction. What's
No,
the,
I was gonna do-
oh, the,
It looks like this afternoon, we're gonna have, Jim was gonna do some examples, a basic closed
Yeah, okay.
economy, and then some computation, which I think would be great.
move to general equilibrium this afternoon. So today is,
Yeah, this afternoon, what do you mean by?
I'm just thinking about, we take a break and then we come back. The question is, when do we want to organize lunch? And do we want to take a break now to maybe get some sandwiches and come
Yeah,
back here?
Tom, what did you have planned for this morning? Did you have something you wanted?
The thing was, my intention was to get involved in teaching a little bit more about the actual mechanics, but Jim is covering that pretty well.
Yeah,
So
I was gonna say, I think if you feel comfortable that he covered, then we
Yeah.
can just go back to this schedule, 1 PM our time. So that would be
2 p.m.
2 PM
DC
their
time.
time. We'll pick back up,
That's fine.
and Jim's gonna go through, right, a bunch of actual examples.
Yeah.
So.
General
one-
equilibrium examples.
General example. So one thing on that, just so everybody is on the same page, is I think we need to, so if you would like to follow along and actually type the code, you're gonna need GAMS Studio, right?
That's right.
And so can you download a free trial online?
That's right.
Mhm.
Yeah.
Okay, so if you go, I think,
It's www.gams.com/download.
okay, gams.com/download, pretty simple. But just try and get that downloaded by, what was it, 2 PM Eastern time?
So in 20 minutes, basically.
No.
No.
Oh,
There's a
Eastern
long
time.
lunch break.
Hour and 20.
okay.
Yeah,
Yes.
you guys got a little bit of time, yeah,
Yeah.
and then that way you'll be able to follow along. I think Jim has code, right?
Oh, yeah.
I think some people probably want to type from scratch, so we might have to try to
Well,
build
I
that in,
have
but.
exercises, which I did on the weekend, so those have not been circulated, but I could.
You can send them to Martha right now.
a-
Yeah,
A zip file of the exercises.
That would be great.
that'd be
And then-
fun.
And
I'll
then,
upload them.
And then Martha will upload them. Natalie, are you able to, can you just send them to Natalie too?